All right. Our next speaker is John Bent. Based out of Los Alamos and a great guy. No, that's sorry. John helps Seagate Gov align future storage software and hardware with large-scale HPC workloads. With colleagues at LANL, Intel, and EMC, John has been focused the past few years on accelerating parallel file systems with flash tiers. Even though I didn't go drinking with him last night, oh man, I'm regretting it now. We're honored and delighted to have John present some of this work to us here today. Man, you know, he was right. I will read anything. Ladies and gentlemen, John Bent.
Thank you, Sims. And I'd like to apologize to everyone for not being able to drink with all of you last night, and Sims. Ruth also, some of you are probably wondering, like, who is this guy? Why haven't we seen him? Why is he just here this week? And it's absolutely not a slight to Lustre. I really like Lustre. I hope to be with all of you next year for more of LUG. And Sims, even though your state has not had the good grace to legalize marijuana, it's absolutely not a slight to Bloomington or whatever state we happen to be in now. I've just been on the road a lot the past 2 months, and my son said, "Dad, please stay home this week and help me study for finals." So that's where I was. I'm sorry. Next year will be better. Now, the good news is, that's nice. Thanks, Sims. The good news is that following my talk, I'll be happy to answer any questions about my talk, as well as any questions you might have about high school physics. I am ready for that. So I'm going to be talking about burst buffers, unraveling burst buffers, talking about some of the work that I've been doing in burst buffers, looking at both the comparison, combining two different things that I've been doing with some colleagues, looking both at a comparison of APIs and of architectures. And although this may not be Lustre specific, I think and hope that it's relevant to the Lustre community. Ultimately, I would like to see Lustre run better on just all flash arrays, right? Why do we need some separate intermediate tier between Lustre and the applications? That does happen to be the world that we're in now, and I am hoping and certainly pushing my colleagues at Seagate to say, let's dispense with this and just move Lustre up into the burst buffer. But for now, we are stuck in a world with burst buffers, and there's some confusion about them that I will hope to help unravel today. This is just a cutesy little thing saying, hey, there's all these different words. What do these all mean? And I'm going to try and clean it up a little bit. All right. So what are burst buffers, just to quickly go through. Now, James had a picture before that he said that people have shown 4 times this week, and it was interesting because he had to label it, and he had to draw an arrow saying, here's where the application runs. And I think that picture is weird, and I think you wouldn't need that arrow, except that you did the picture upside down. So when I think of these things, hey, where's the app? It's at the top, right? That's the way I've always thought. So I don't have an arrow saying here's where the app is, because my picture is right side up and it's not needed. So you've got compute nodes at the top, you got a parallel file system. What's burst buffer? You just slide in some nodes, right? You slide in some flash or some other accelerating media. Your job is running up on those compute nodes, it's producing data. It very quickly puts the data into the burst buffer, and then 2 things can happen, right? It can simultaneously move on and compute new data while the data asynchronously drains from the burst buffer tier to the parallel file system tier. Okay. So how do applications access burst buffers? And in this slide, I'm calling them tiered storage, which is sort of a concession. Some of this work came from an exploration of the burst buffer APIs that I did a couple of months back. DOE had a workshop about burst buffers, and they decided to call it tiered storage. And I think that makes sense. I think burst buffer is an unfortunate term that carries a connotation that isn't always appropriate. So I remember I was working with some of the folks at Intel on the Deos project, and I was at EMC working on the burst buffer thing. I'm at Seagate now, but I was at EMC working on the burst buffer piece of that, and I would go around and talk to scientists, and I'd say, hey, we've got this burst buffer thing, and they'd say, oh, well, I don't care about burst buffers. And I'd say, well, why not? And they'd say, I don't checkpoint. I'd say, oh, okay, well, tell me about your workload. And they'd say, well, I like run a simulation for like a really long time, and then periodically I pause, and I'll take all of the state and memory and save it down into the storage system. And then I'll repeat that cycle. So I said, well, you know, actually you are interested in burst buffers. But so we decided not to call it burst buffers, call it tiered storage or flash acceleration or something like that. And I think it also implies that the workload needs to be bursty in order to benefit from a flash acceleration tier. And intuitively that makes sense, right? Because you need some time in the background to drain. But actually there are some workloads, that's not what I'm going to talk about today, but always interested in talking about it. I think there are instances in which even sustained data benefits from a flash tier. You know, and one easy thing is doing aggregation and changing and pattern shaping, traffic shaping. So back to this slide, how do applications access tiered storage? And there's sort of three ways, I think, right now. There's middleware. There's a whole bunch of middleware libraries, Argonne, Lanel, Livermore, HDF5, Oak Ridge, and maybe Intel's Deos is one as well. I don't know, maybe it's instead a replacement. There's also direct, right? So that's Cray and DDN, EMC. This is something that I was working on when I was at EMC, this two tiers thing. And IBM has a burst buffer that they're putting onto Coral. And then finally, there's sort of block level flash accelerated storage. So this is inside the storage arrays themselves. So DDN's got something, Hitachi, Seagate has this Nitro thing, and even ZFS, I think, with some of the allocation class, is looking at using flash accelerated storage, right? So in the Lustre world, right, your OSTs have some flash and some disk and internally are doing some smart tiering. So what I'm going to be talking about today is not the middleware nor the block level, but really focused on those direct API, the direct burst buffer instantiations, the Cray, the DDN, the EMC, and the IBM. The middleware and the block level, one of the reasons I didn't look at them, because I was really looking at how do applications interface with these. And both the middleware and the block level are sort of hidden from the applications. I was actually really surprised when I discovered this. I was talking to a bunch of the middleware developers, you know, Argonne and Lanel and Livermore, and they said, well, I said, well, what is in your API to allow users to pass hints about directing or even, you know, explicit control of the data movement across the data tiers, the storage tiers? And they all told me, like, hey, we don't do that. We hide that. Right? We're an abstraction. So I said, okay, well, I'm not going to study you then. And then what about block level? Is that something that's maybe part of this study in terms of how do applications access it? And, you know, maybe we should say that, yeah, absolutely, right? A block level is tiered because you got multiple media with disparate characteristics, and it does tiering. But it's invisible, and maybe it's not manageable, right? For that same reason. But I think we're looking at doing things like Intel's DSS, and moving hints, but it's going to be complicated, right? Because that tiering is done at block, but if users want to be involved, obviously they don't know the logical data to block mapping, so we're going to have the file systems themselves involved. Okay, so turning to really what I looked at, which was the direct ones, and it's the four, the IBM, the Cray, the DDN, and the EMC. How does the user then interface with those four systems, right? And one is you can interface through the workload manager, put directives into your job submission scripts, through a command line interface, or through a runtime, right? And the runtime's MPIO or POSIX, or a direct API, right? So if you're using Cray Data Warp, your application might write data warp underscore whatever. Or that's what I thought, and it turns out there's not much of that. So when I initiated this, right, when I started this exploration, I really thought I was curious about the direct API. I want to see what they've gone through and they've taken out the open read write close of POSIX and have replaced it with data warp underscore open or IME underscore open. That's what I really wanted to study, and it turns out they didn't really have any of that. That all the IO is actually going through POSIX and all the control is going through the workload manager. So the direct API wasn't a part, it didn't end up being a part of my study. It's just not there. And the observation is, well, first of all, you know, we all bow down to the almighty user and we respect their desire to be unperturbed. And that's what we've done, and we allow them to continue using burst buffers. And so burst buffers, tiered storage, flash acceleration, is really about the control plane and not the data plane. So we've got these interfaces. What are they used for? And they're used to initialize, right, to set them up. They're used for policy, to say when and how to tier. You create the mount point. You can do the staging, right? You initiate the staging. Hey, before my job runs, this is the stuff that needs to be ready. After my job finishes, this is the stuff that needs to be preserved. Directory operations and file operations. So sometimes when I make slides, I try and imagine my audience, and there's two audiences for a slide deck, right? There's you guys here in the audience that are listening to me today, and there's also the reader. So there's a lot of information on the slide, and I'm going to say that a lot of this information is for the reader, but we'll go through it a little bit now. What it is it's a table, right? And it's saying here's all of those different things that we can talk about doing to a tiered storage system, right? In the key in the bottom, you can initialize it, you can set the policy, pre-stage, mount and directory and file, and then those columns are the different interfaces, right? So the key is what you can do, and the columns are how you can do it. And then the color is there documentation that's available and what that documentation looks like. And really the observation here again is that in the application API, in the runtime, there's nothing about directory operations and file operations. So it's again, the same point that I made on the previous slide. Okay. So for setting up tiering, so the parentheticals, we have the four that we talked about, the EMC, the DDN, the CRAE, and the IBM. But DDN doesn't have documentation available. So what you see in the parentheticals is of the EMC and IBM and CRAE, how many of them support a particular feature. And by the way, EMC is not productized, but they spent a lot of time thinking about this interface, so I thought it was useful to include it. So what can you do? You can specify which directories to stage. All of them do that. Looks like you can set throttles, and one of three allows you to set a throttle on your bandwidth. One of three allows you to set throttles on your concurrency, set I/O limits, but with different combinations of read-write bytes, I/O per time period, the file size, the number of files, quotas. You can set up striping and sharing. One of them does that. You can disable and enable automation. That's the implicit or explicit tiering. And by the way, this isn't my intention to say this one is good or this one is bad. It's really just to open our eyes as a community to what's possible right now and learn from all the different instantiations and try and figure out, this is early days still, which features are useful. Set the tiering policy. You can do it every so often, or you can do it on sync or on close or at job end. Set up the lifetime of your data. So what do I do, Sims? Really? Pretty good. Oh, but I got to start over. All right. I won't talk through it again. Okay. Set up the lifetime. So one of the earlier talks this morning was talking about producer-consumer type relationships of data. So sometimes you want your data to live beyond the end of your job. You can do that. Sizing. Okay. You can set the size and grow it. So just to sort of do a whirlwind tour of some of the stuff, there's some cool features, I think, that aren't available in the APIs, right? They're cool features of management that you can only do in the job schedule or at the command line. So things like setting up the allocation or the namespace, whether it's shared or private, the tiering policy that we talked about, and the optimization strategy. So clearly something that's very important with using flash tiers, which we didn't really have with hard drives, is the durability and the drive writes per day. And it's useful to be able to control that, either certainly for the administrators or for the users. So they all had mechanisms to query the SSD health and to try and set up policies to load balance across the SSDs, not just for performance, but for lifetime. So again, the observation is it's all about minimizing application modifications. You're doing things through the scheduler, the command line in POSIX. And the API is just sort of like for tier now or tier later or kill. EMC does have some setup in the API. Okay. I'm not going to, again, this is a slide for the reader, so I apologize to you, the audience, but just to know that this slide is available, and it talks about setting the thing up and how you can do it in the command line and in the API and in the job scheduler for IBM and EMC and Cray. So you can see some of those, not applicables, right? You can't do it. So staging a file, they have ops on staging transfers. They're all asynchronous. They all allow you to query. 2 of the 3 allow you to cancel. 1 of the 3 allows you to list what's going on. 2 of the 3 let you submit in batches. 1 of the 3 let you say block until this thing happens. The other 2 you'd have to poll. 1 of the 3, and this is interesting, we'll talk about it in a second, has key values. And 1 has concurrency for directory staging, right? So you say tier this directory and all of its subcontents, but only do 100 threads at a time or whatever. Okay. So staging terminology, this is just what does everyone call it, right? We haven't converged as a community on the terms. So this key value attached to a transfer, I said that was an interesting feature. This is something that IBM does. When you do a stage, you can say, hey, create some stage operation, and you get a handle back to that stage operation, so you can say kill it or what's going on or how far is it or to set the concurrency on it. But you can also add key values to it. I thought, well, that's weird, right? Why would you want to add key values to it? And apparently some of the labs asked for it. They wanted to say, this staging operation is checkpoint 13, for example. Okay. Cray has an interesting feature, which is called get MDS path, which is a little weird. I think it's slightly poorly named. It's a cool feature. To me, it suggests like it's saying get the path to the MDS, but rather what it's saying is you have a whole bunch of paths, and each is served by a different MDS. And so you can say, I want to know, it's to allow the user to do load balancing, right? Oh, and so what it does is Cray will hash on an object name or a file name to a particular metadata server. And so then you can say, I've got these 20 objects. I want to know, are they spread across 20 MDSs or 3 or 5 or 7 or what? So a closer look at SSD protection. Both IBM and Cray have mechanisms in place for protecting your SSDs, so you can set the usage limit. And Cray does sort of interesting things where they say no more than this many bytes within this many seconds, or no files larger than some size, no more than some number of creates, no more than some number of total bytes. Then what happens, right, when your application, right, the I/O is through POSIX or MPI/IO or something, the application's just going to get a write error if it tries to exceed these quotas. API throttling, we're not really going to go through this, but there are mechanisms to do the throttling. And they're interesting, right, because one throttles with the number of streams and the other throttles with the bandwidth rate. Okay? But they're both for that same purpose of protecting the SSDs. This is a slide for the reader. How does job submission work? And basically what you do is you just put a bunch of stuff into Slurm or what's the one that IBM uses? PBS? Load leveler, thank you. And then what you get is then your application uses environment variables. Right, so all you have to do is change the path for your POSIX applications or your MPI. So that was a comparison of burst buffer APIs. So just slightly differently, we're again comparing, different burst buffer aspects. And this is different burst buffer architectures. And this is work that I did with some colleagues at Los Alamos, and we called it to share, not to share. It's actually a combination of a couple of different things that we've worked on. So, hey, we've got this, and this one is also not upside down. It's not right side up. This one's left right, but it's still better than James's upside down thing, at least. And what you have is you have the supercomputer. Thanks, Andres. You have the supercomputer on the left. On the right, you've got the storage system, and you got some I/O path. So we want to do burst buffers or tiered storage or flash acceleration. Where do we put the flash? Well, you could put it on the compute nodes, right, like what Cray and Intel are doing at Argonne. You could put it in the middle, like what Lanel's doing with Trinity. Or you could embed it inside the storage system, like what Seagate is doing with Nitro. So let's talk a little bit about those different choices. So we call the compute node, we call that private. And there's certainly more than those three, and there's variants of those three, and there's different ways to do those three. But just bear with me for a little bit, and this is at least one way to do it. So the node local, we refer to it as private. It wouldn't, the reason I went into that big thing about how there's different ways to do it, node local doesn't necessarily have to be private. But for the purposes of this, we're going to assume that if it's node local, it's also private, meaning that it's really just visible from the node on which the flash is hosted. So what are advantages? There's no contention. You got linear scaling, right? The more compute nodes you have, the more flash acceleration you have. It's cheap, right? You don't need to buy new nodes. You've already got the compute node. You just throw some flash on there. Intel, gives it away, right? So that shouldn't be too expensive. There's no network bandwidth. It's totally local. I don't know why Peter's laughing at that. There's a disadvantage, which is that there's a coupled failure domain, and we'll talk about that in a second. Single shared file is difficult. The N-to-1 I/O is challenging. And a small job, you can't use them all, right? That's sort of related to the linear scaling advantage. So shared, the ones in the middle, like what Lanel's doing with Trinity, plenty of other places are doing it as well. N-to-1 is easy. The single shared file is easier. The data can outlive the job. It's in a separate location. It also provides temporary storage if your parallel file system is offline. Small jobs can use it all, right? It's all visible to everyone. You have a decoupled failure domain, and again, we're going to delve a little bit deeper into what that means. It's the most flexible ratio between compute and burst buffer and parallel file system. You can get exactly the amount that you want. Now it's most expensive, maybe, because you need new nodes in addition to just, getting some flash into the system. Now I think in some of the architectures you're putting it into existing I/O nodes, so maybe it's a little bit cheaper. Okay. Interference is possible. Oh, and that's it, and interference is possible. So embedded, right, inside the storage system. This is very similar to shared with a few differences. So the differences are italicized. So N-to-1 is easy. That's not italicized. That was the same as shared. The data outlives the job, same. Small jobs can use it all, same. Decoupled failure domain, same. I'm sure we got some in here somewhere. Low cost, that's italicized, right, because you've already got the storage, so it's cheap to throw some flash in there. Intel probably won't give it free to us, though, right? And it's most transparent is an advantage. So disadvantages, well, this is a new one. The storage area network has to be provisioned for the burst bandwidth instead of the drain bandwidth. Interference is possible, that's the same. And I've listed also as a disadvantage that it's most transparent, right? So that's both potentially an advantage and a disadvantage. So let's talk about, we had those advantages and disadvantages of coupled and decoupled failure domains. Why are we talking about that? What does that mean? So a coupled failure domain, when you've got this node local burst buffer, that when the job fails, the last bursted checkpoint is also lost, right? Which means following a job failure, you always have to go back to the last drained checkpoint. So remember, my first slide after the title, we said the job makes data, it puts it to the burst buffer, then it moves on to the next data phase while simultaneously the bursted checkpoint is draining to the parallel file system. So with coupled failure domains, you always have to go back to the last drained, or you can parity protect your burst buffer. Now, parity protecting your burst buffer is a little problematic because one of the advantages that we saw for private was that you weren't going over the network. You just had like this really nice high-speed bandwidth to the local attached storage device. But now if you want to decouple the failure domain, you have to be over the network to send parity. So the decoupled failure domain, when the job starts, the last bursted checkpoint is still always available when the job fails. when the burst buffer fails, the job can just continue, right? They're decoupled. Now, this does assume maybe some failure resilience that isn't built into the systems today, but I would argue should be. And so the implication is that decoupled doesn't need parity, all right? So we've got some results from hot storage a couple years ago where we looked very deeply at this one question. We had a model, so the y-axis is the overhead due to checkpoint restart. So specifically what we looked at was you have 24 hours of compute that you want to get done. But in order to get it done, you've got a checkpoint restart. And so maybe that checkpoint restart costs you 2.4 hours or something of checkpoint restart time. And so now the overhead, right, you did 24 hours of compute and 24 hours plus 2.4 hours of time is 10% overhead. So that's what the y-axis is. Then the x-axis is what's the overhead of having a reliable burst buffer. So, you know, the 20% overhead might be RAID 10 plus 2, right? So you need to protect your burst buffer, and in doing so, it's going to slow down your checkpoints, right? Or 100% would be two-way replica. The line goes down to 0. Of course, that's not a possible number because you can't make a reliable burst buffer with 0% overhead. Now, some people are doing interesting things like, or are thinking at least about doing interesting things like doing an unprotected checkpoint really, really fast, and then maybe asynchronously trying to add some parity. But that's not what we're looking at here. So then what we did is we compared that to using an unreliable shared burst buffer, right? And so it's a flat line because it's unreliable. There is no parity, so it's actually independent of the x-axis. So what this shows, right, is that it doesn't make sense to have a reliable burst buffer, right, if it's in a decoupled failure domain. Just don't even bother putting parity, and your total throughput of all of your jobs will be faster. Caveat, assuming some resilience that we don't have. Lots of details in the paper. So that was all actually we had in the paper, and I have to admit it was one of my best ratios ever of work to publication. It was just a couple of formulas in GNU plot. Since then, I did add another formula to the GNU plot, looking at if it's a private, if it's a failure domain coupled burst buffer, what happens if it is unreliable? And what you see is that there's a lot more overhead. So the observation is that if you have a shared burst buffer, right, in a decoupled failure domain, it doesn't make sense to add parity, you know, for checkpoint restart. And I would argue actually for most data, right? I think most data that's going into our HPC burst buffers can be deterministically recomputed. So I would think for a lot of data, if you've got a decoupled failure domain burst buffer, it doesn't make sense to parity protect it if all you're concerned about is the total throughput of everything that you're doing over the course of a year. Okay. Private does need parity, but the problem with adding parity to private is that then you lose the advantage that it's directly connected and potentially at higher performance by being so. Okay, so to change, this is another thing that we did looking at these architectures. This one we did with simulation. We took all of the Apex workloads in the Apex Workflows white paper. We ran a simulation of running all of them on Trinity. So it was like a couple of months of computation with a mix of all the different workloads as described in that Apex Workflows white paper. And this table just shows what the mean checkpoint bandwidth is. So if you had local unreliable burst buffers, which again I would say is problematic, if it's local it should be reliable, your average checkpoint bandwidth was 200 gigabytes per second. If you add parity like you should for throughput, obviously your bandwidth's going to go down. And then the last thing is that if it's shared, that means that small jobs can use the whole thing. And your average checkpoint bandwidth goes up by a factor of 3 or 4 even, right? So the observation there is that if you're running a capacity machine with a mix of jobs, you should do shared burst buffers. And then you should look at the work coming out of Oak Ridge, where they're trying to figure out how to stagger the jobs so that they checkpoint at different times to ensure that the small jobs can always benefit from the full burst buffer bandwidth. And that's it. Thank you. I was joking about high school physics. And my poor kid is going to fail horribly.
Any questions?
I'm headed towards Corey Spitz right now.
Hi, John.
Hey.
So you didn't cover this in the talk, but at the outset, you talked about your desire to move Lustre up into the burst buffer. So I was kind of wondering what you see that isn't obvious or done there. That is, what are the barriers to doing that?
Yeah, I love that question. I wish I had a better answer. I know that anecdotally people try and run Lustre on all flash arrays and they're not getting the efficiency of the hardware that they would like to have. I hope that changes. I hope I'm wrong, but that's what I've seen, and I know that we're seeing that same thing. So we're looking at it. I mean, what does that suggest? I mean, it suggests it's got to be the software. I assume it's metadata, bottlenecks, and locks, but sorry. But boy, can anyone else answer that? So I gave a talk, how many years ago, Andreas? It was horrible. He's laughing. I'm still upset with you about that. At LAD a couple of years ago, where I was giving somebody else's slides and I had no idea what I was doing. And so I just put the slides up and read them and there's questions. And Andreas had to bail me out every single time. So can you bail me out on this one?
He said you're right. That was all that was needed, evidently.
All right. Ladies and gentlemen,